Okay, calculus. We have been talking about where a graph is increasing and where is it decreasing, and where are the local maximums and the local minimums. I did a video on answers to some of the homework. Hopefully that helped. If you're still struggling, please let me know. Someone let me know first thing this morning that 6.1 was still an issue, but I don't think the video had gone up yet on the answers that I had done to 6.1. So hopefully that helped. If it didn't, please be contacting me and letting me know that you're still struggling. Because we're gonna build again today. So far what we know is that graphs can either increase, which means goes up, or decrease, which means goes down. And there is a point at which it changes. The point at which it changes from increasing to decreasing is a local maximum. And the point where it changes from decreasing to being increasing is a local minimum. And both of those are what we call critical numbers. They are numbers where something in the graph changes. It changes from going in one direction to going to the other direction. That tells me a little bit about the shape of the graph. It gives me a good idea about sketching the graph, but it doesn't give me all the information. One of the other things we want to talk about is the idea of concavity. Concavity. And basically what that means is something concave up or is something concave down. So let me show you what I mean. If you have a graph that does this, okay, that graph is always increasing. It's always going up. So if I were to take the first derivative, make it equal to 0, what I would find is there were no local maximums or local minimums. The graph was just always increasing. But I wouldn't know that there was a curve to it. For all I knew, it would be a straight line. So how do I know about this curve thing? All right. What that is that is the concavity. This would be considered concave up because it's like a smiley face, right? It's going up. Concave down, I can still draw a graph that is increasing, but this one is slightly concave down, all right? Still always increasing, but it is concave down. A graph can even switch from one to another and never change direction. For example, this graph right here, this is always increasing. As I go across, it's always headed up. So this graph is always increasing. But for this part of the graph, it's concave down. And for this part of the graph, it's concave up. The point at which a graph changes from being concave one way to being concave the other way is called a point of inflection. So a point of inflection is where the graph changes from being concave one way to being concave the other way. So how do I know which way it is and where all that happens? And by the way, on a graph, it can be very subtle. That point of inflection, you may not even really be able to identify where that happens, because if it's something very, very subtle, see, it's sort of concave down here and it's concave up here ever so slightly, but where is that exact point where it switches? It's really hard to tell off the graph. So how do I do that? Again, there's a method for this. So going back to section 6.1 and 6.2, to find where a graph, to find where a graph is increasing or decreasing, you take the first derivative, you make it equal to 0, and then you do your test points. To find where a graph is concave up or concave down, you do something very similar, but this time you take the second derivative, and then you figure out, you make it equal to 0, you do exactly the same thing, you make it equal to 0, and if it turns out to be positive, if one section turns out to be positive, that means that section is concave up, and if it turns out to be negative, that means it's concave down. So I'm going to do example 1, I'm going to do example 2, but just A and B, and then we're going to put everything together in example 4. I'm skipping example 3 because I think it is needlessly hard. Like, it's stupid hard for no apparent reason. What it does is it brings in the idea that of the quotient rule. So you're doing the second derivative with the quotient rule, and it's just, it's no different, but I find for explanation purposes, it just serves to confuse you, because I lose you on the derivative part, which isn't even the whole point of the question. So we skip it. So we're going to do example 1 on page 332. We're going to do example 2, A and B, also on page 332 and 333. And then we're going to skip over to example 4, where we're going to put everything together. All right. So in example 1, it says, show that the function f at x is equal to x to the 4th. Show that it, and I'm paraphrasing here because the language they use is confusing, but show that it has no point of inflection. Show that it has no point of inflection. So again, what I'm going to do is I'm going to look for points of inflection. So we take the first derivative, which would be 4x cubed. Now, if I was looking for where is it increasing and where is it decreasing, I would then make this equal to 0 and solve and do my test points. But we're not looking for increasing or decreasing this time. We're looking for points of inflection. We're looking for concave up and concave down. So I'm going to find the second derivative, which would be 12x squared. I'm going to make that equal to 0. 0 is 12x squared. I'm going to solve. So I'm going to divide by 12. I'm going to divide by 12. And I have x squared is equal to 0. So x is 0. So that is my potential point of inflection. There might be a point of inflection where x is 0. But let's find out if there is. So I'm going to pick a number less than 0, -1. I'm going to put it back into the second derivative, because when you're talking point of inflection, you're always looking at the second derivative. So I'm going to pick -1, I'm going to put it in here, and I'm going to see, do I get a positive answer or do I get a negative answer? So -1 squared is 1, times 12 is 12. I get a positive answer, which means it's concave up. So then I'm going to pick a number after 0, like 1. 1 squared is 1, times 12 is still positive 12, so it's still concave up. So while it looked like I had a potential point of inflection there, a point where it changed, it actually doesn't change. It actually stays the same. All right, so their point is that it could look like you potentially have a point of inflection, but you really need to check it and see, because it isn't always. So example number 2. Example number 2 says, determine where the curve f at x is x cubed minus 3x squared plus 5x plus 2. Determine where is it concave up and where is it concave down, and part B says find the point of inflection or points of inflection. There might be more than one. So I'm going to find the first derivative, which is 3x squared minus 6x plus 5. Isn't it nice that we can do those that quickly in our heads now? Remember back when we were doing derivative by first principles? So much easier. But first derivative we use for talking about whether the graph is increasing or decreasing. And they haven't asked me about that. They've asked me about points of inflection and where is it concave up and where is it concave down. So to figure that out, I'm going to do the second derivative, which would be 6x minus 6. I'm going to make that equal to 0. And I'm going to solve. So 6 is equal to 6x, and so x is 1. So I have a potential point of inflection where x is 1. I don't know if it is yet because it could be like the last one, but I'm going to check. So I'm going to pick a number less than 1, like 0, and I'm going to put it into the second derivative. 6 times 0 is 0, take away 6 is negative 6. So I get a negative answer, which means it's concave down. I'm going to pick a number after 1, like 2. 6 times 2 is 12. 12 take away 6 is positive 6. And because it's positive, that means it's concave up. Okay, it's switched. Because it's switched, that means there is a point of inflection where x is 1. But where is that on the graph? What would be the y value? Right? 1 and what? So that means I have to take that 1 and I have to put it back into here because that is my y value. So 1 cubed is 1, minus 3 is negative 2, plus 5 is 3, plus 2 is 5. So I would have a point of inflection at 1 and 5. So before 1 and 5, it would be concave down, and after 1 and 5, it would be concave up. All right. So again, no matter how hard the derivative gets, whether you have to use the product rule or the quotient rule or whatever, when you're talking point of inflection, you have to find the second derivative. All right. So example number 4. Oh, and they talk about something called a second derivative test. This is the second derivative test. It says when I pick a number, when I pick a constant, if I put it back into the second derivative and it works out to be negative, it's concave down. If I pick a number, a constant, and I put it back into the second derivative and it works out to be positive, that means it's concave up. So they talk about, they use fancy words like the second derivative test. This is the second derivative test. It's nothing big, okay? So example 4 on page 336. So now is where they're going to put it all together. So what we're going to do is we're going to take an equation without ever doing a table of values. We are going to draw a sketch of this picture just using the skills that we have so far. So it says you have the function y is equal to 1/4 x to the 4th minus 2x cubed. The directions say find the local maximums and minimums and use these with concavity and points of inflection to sketch the graph. So I'm going to be looking for several things. I am going to be looking for any local maximums. I'm going to be looking for any local minimums. And I'm going to be looking for any points of inflection. So local max and local mins are where does it change from increasing to decreasing or decreasing to increasing. So that talks about the first derivative. So the first thing I'm going to do is find the first derivative. I'm going to do it over here. Y prime, if I bring this down, that's 1. So that's x cubed minus 6x squared. I need to find local maximums and minimums, so I'm going to make that equal to 0. And I would factor this. I would take x squared out, so I have x minus 6. So either x squared is equal to 0, which means x is 0, or x minus 6 is equal to 0, which means x is 6. So doing my little table, I have 0 and 6. And they didn't tell me a start point or an end point, so I assume that this graph is continuous. It goes on forever in both directions. So I'm going to pick a number before 0, like, I don't know, -1. and I'm going to put it back into the derivative, and I'm going to see, do I get positive or do I get negative? So if I do negative 1, this would be negative 1 minus 6, which would give me a negative answer. So before 0, any x values before 0, this graph is going downward. Between 0 and 6, anything I want, so I'm going to pick 1. This would be 1 take away 6, which would still be negative, so it's still going down. So that is not, Willow, you're fine. It's okay. So that is not a local max or a local min because it didn't change direction. And so then I'm going to pick a number after 6, like, I don't know, 10. 10 cubed would be 1,000. 10 squared is 100 times, so this would be like 1,000 minus 600. So that would be positive, so it's increasing. So I have a local minimum here. I don't seem to have a local maximum, right? I don't have a place where it's increasing then decreasing. So I don't have a local maximum. There isn't one. All I have is a local minimum. And that happens when my x is 6. I'm going to put it just above because I don't have a lot of space there. So it happens when my x is 6. So I need to know what would my y value be because I'm going to want to put this on a graph. So I'm going to take that 6 and I need a y value, so I'm putting it back into the original to get the y value. So I'm going to go 6 to the 4th times 1/4 minus 2 times 6 cubed. I'm going to cheat because I can. It turns out to be negative 108. So that's really low. And now I have figured out everything I can about local maximums and local minimums. Now I need to talk about points of inflection. Points of inflection mean I have to do the second derivative. Okay, so second derivative means I'm going to take the derivative of the derivative. So this is going to be 3x squared minus 6x. I'm going to make it equal to 0, and I would actually take 3x out as a common factor, so that would leave me with x minus 2. And so either 3x is equal to 0, which means x is 0, or x minus 2 is equal to 0, which means x is 2. So I'm going to set myself up another little doodad where I've got 0 and 2. I'm going to pick a number before 0, like negative 1. I'm going to put it back into the second derivative. So negative 1 would be, this would be 3 plus 6. That would end up being a positive number, so it would be concave up. Between 0 and 2, well, I'm going to pick 1. So this would be 3 minus 6, which would be negative 3. So it's negative, so it's concave down. Notice it has switched directions. So there is a point of inflection when my x is 0. Let's continue. So I'm going to pick a number bigger than 2, say 3. 3 squared is 9. 9 times 3 is 27. And 6 times 3 is 18. 27 minus 18 is a positive answer, which means it's concave up. So again, it's switched again. So there's a second point of inflection when my x is 2. So I need y values for those. I need to know where would I put that on the graph. So I'm going to go back to here where y is equal to this. I'm going to put 0 in. If I put 0 in here, I get an answer of 0. And if I put 2 in here, I get an answer of, oh wait, apparently I made a mistake. Big shocker. Yep, did you find my mistake? Were you yelling at me this whole time? I hope you were. I hope you were. So just hold on. When I did my second derivative, this is 3x squared, but if I bring my 2 down, this is actually minus 12x. And so when I took 3x out, it would be x minus 4. So this would be x minus 4. So this would be x is 4. So this is 4. So again, not a big deal. But I need to pick a number bigger than 4. So I'm going to pick 5, because I can. 5 squared is 25 times 3 is 75, and 12 times 5 is 60. So 75 minus 60 is positive, so it goes up. So the point of inflection, my mistake, is actually at 4. So, and that was me making a stupid mistake that hopefully you were like so frustrated screaming at your screen at me. So I would take 4, sorry. I would take 4 and put, I told the grade 9s it's harder to control this group than it is to control like my students at school. So I put 4 back into here, and it turns out you get negative 64. So I now have a picture of what this graph should look like. I'm going to erase this because I need the space. I'm going to keep this though. So here's what I know. Here's what I know. I know I can make a sketch of this because I know I have a local minimum at 6 and negative 108. So obviously this is a sketch. So we'll say 6 is here and negative 108 is down here. All right. If that's a local minimum, that means it goes up on this side and it goes up on this side. Now, it said it was concave up after here. So I don't have that thing anymore, but it had 0 and 4, and it had that it was concave up, then concave down, then concave up again. So at 0 and 0, it switches from being concave up to concave down, but it's still headed downward because this was 0 and 6. So all the way to here, the graph is headed downwards. But there's a point of inflection here, meaning it's going from being concave kind of up to concave down. Now at 4 and negative 64, so again, this is a sketch, so we'll call that 4 and negative 64. Okay, so at 0 and 0, it switches from being concave up, which that is, headed up, to being concave down, so concave down, so concave down. And then at 4, it switches to being back to concave up, so back to concave up. All right, so I have given a basic picture of what this graph would look like, just based on knowing where my local max and mins were and knowing where my points of inflection were. I'm going to leave it at that. I'm going to give you some questions to try on your own. Not a lot, just a few. Let me look at the directions just in case. Nope, that's fine. 5 is easy, and 8. Yep. So make sure you read the directions. I'm only giving you a few to try, and I'm going to give you until Monday to have that done. All right, so Monday morning, I'm going to be looking for the answers so that if there are questions, I can make a video on it or talk to you about it or whatever I need to do. All right, so I won't be making another video for Friday unless you have questions that I absolutely have to answer right away. So I probably won't be talking to you until Monday. So if not, have a good weekend, guys.